Thank you.
long distance travel. And he's in the Applied Science and Arts Northwestern Switzerland School of Applied Psychology. He's the co-founder of a private consulting company in Zurich, Switzerland, and a senior consultant. He is also going to be talking today on humans, disturbing factors, or critical resources in socio-technological systems. And so that's a big word, socio-technical systems. I'm going to be learning something today, Dr. Wäfler. He is a lecturer and researcher at the University of Applied Sciences and Arts Northwestern Switzerland. He's the School of Applied Psychology, where he established the Institute of Humans in Complex Systems. The institute conducts research projects in the domain of human factors, socio-technical system design, collaborative planning processes, occupational health safety, and security. Very important occupational health safety, especially even in chemistry. Excellent. And then he's also in 1990 was the co-founder of the IRWA GmbH company. Is that correct?
Yeah, it's limited.
And a private consulting company in Zurich, Switzerland, where he is still a senior consultant. As a consultant of his topics, he includes organizational job design and highly automated work systems, with a main focus on process efficiency and reliability, as well as system safety. So I welcome you, and I'll let you take the floor from here and tell us more about your research.
Thank you very much. I'm very happy to have the opportunity to give this talk here today. I was invited to talk about socio-technical systems, and I was choosing the title Humans, Disturbing Factors or Critical Resources in Socio-Technical Systems, as we see that the humans very often are considered to be the disturbing factor or risk factor, makes potentially mistakes, gets sick, does something wrong, suffers from fatigue. And very often in socio-technical systems, when we see technology being implemented, technology is meant to replace that risky factor human, or at least to control human behavior. And of course, human are a risk factor, but human also provide positively to the system performance, and I'd like to emphasize in my talk much more on that side. I'm having a psychological background. I'm a psychologist by education. I studied psychology, computer sciences, and economics, and that puts now a psychological perspective on the subject matter we are discussing at this conference, and I hope you don't find this too strange. So, but let me first introduce or present the institute I'm representing here. Within the School of Applied Psychology, we have an institute we call Institute Humans in Complex Systems. And what we do there is we analyze, we evaluate, we try to find out how to design complex systems in the domain of work. So we are looking at work mostly or only. And these systems are becoming increasingly complex because of complex technology and also because of complex processes and organizational structures. And now our objective is to understand how to design the systems. I mean, the systems, not the technology, but the humans and the system in combination, so that they can operate reliably and safely. And the special focus, of course, of the human contribution to reliability and safety. So our question is how to design the system such that the humans working in the system can provide to the reliability and the safety of the systems. We have a lot of projects with industries. This is one of manufacturing, and you will see that in the examples I bring. And also we have projects in high-risk industries where we deal with human factor and safety management in nuclear power plants in Switzerland and also in aviation. So that's our background. Now, the outline of my talk, I will first give you some examples about socio-technical systems. I will do that on two levels. Level one would be level human-machine interaction, means an individual with technology. And level two would be more on the organizational level, where we have social systems interacting with technical networks and how do we fit them together. And I use that part of my talk in order to illustrate where we see the problems. And actually, you just tell me if I tell you a lot of old coffee or already know, because I don't know what is your knowledge in that domain already. Then I will talk a little bit about the human positive contribution to system performance, and and introduce or design principles. So what do we learn from our science, how to design that systems? And I give you just some examples. I cannot go too deep into the details, but just to give you an idea how we approach the topic. And of course, I will finish with a summary. I'll start with my examples. That was a project we had some years ago with a Swiss manufacturer of artificial joints. I mean, artificial hips and knees and elbows. And when producing these joints, the ball up here of the joints needs to be grinded. And grinding is not an easy task with that metal because it's a complex mixture of different metals. And how they did it at the beginning of the project, they had machines like that, and it was like 20 of these machines in a row, and 20 human operator taking the joints and holding it at the machine. That's how they did the grinding. And all these 20 people were not formally educated. They were blue-collar workers, helping hands, most of them immigrants from southern European countries. We didn't actually care about them because we were interested in the grinding. And we were working at our university. In that time, I was at the Swiss Federal Institute of Technology, together with our engineers to build a robot who can replace those humans because, you know, they make mistakes and they do not meet the quality once in a while. And we were building that ourselves. And then the robot was programmed to take the joints and held it against the grinding machine. And we were not successful. That means the quality of our grinding was never meeting the quality standards, whereas the quality of the grinding of the humans did. That's when we learned, we know how to program a computer, but actually we don't know at all how to grind. We have no knowledge about the grinding. And these humans we didn't even talk to so far, they seem to have something, a dexterity or an art in their hands coming from years of experience of knowing how to do that. So when they ground, the quality is fine. Our robot did not meet the quality. So we thought about, that was our first insight. There is a knowledge, a tacit knowledge, which is important for the quality of our products. We didn't even know that we have that knowledge. We only realized it when we lose it, but we didn't know that it was there. So the question then is, how did we put in the knowledge into the robot? And we had a good technical idea. We added a joystick to the robot and asked one of the helping hand to control the robot, to show him how to do it. And the robot was with a teaching system learning that and creating a program out of that, and then it worked. So that helping hand could do that in a way that the robot was able to meet the quality of grinding. Then we thought, okay, now we have their tacit knowledge in the machine, and now we can get rid of them. Then we realized, now when we come with new joints, because they permanently develop new products, with the humans, we just go there with the new joint and try how to grind. And then they try and figure out how to do it best, and finally they can it. That doesn't work with the robot. So we had a second insight. It is not only the tacit knowledge that we have in the human hands, even more in the hands than in the heads, but it was also the further development of that knowledge, the innovation that we lose when we put all in the robot, because the robot does not create any innovation. It just fixes what we have, and that is the end of the history. So we have three problems. There is knowledge, tacit knowledge, that only comes from experience. We have a loss of innovation if we put it in the machine, and also we have a de-skilling of the people if they do not do it anymore themselves. That's all what we learned. And of course, I mean, this is an example from automating manual work, but we see the very same also now when everybody's talking about fourth industrial revolution, where we digitalize all the business processes, also the administrative and the planning process, also cognitive work is automated, and we expect the same problem there. And we have already seen, for example, the human planners, if they produce a plan, if they do it, so to speak, manually or cognitively, then they know how plans are created, and they have a tacit knowledge there too. And that makes them, when they are very experienced, just to have a glance at the plan and see, oh, here we have a problem. Whereas I don't understand anything. And now the young generation does not make the plans anymore, because the plans are generated automatically by the IT system, and they lose the knowledge to good interpret the plans because they don't have it anymore. So that is one example. I bring you another example I would like to show with that picture. Very often what we see when there is automation, the automation is running without the human, if it runs well. And the human's task is to be sitting up here in this glass box, and in case of emergency, jumping out and saving the system. And one problem we have there, we have several problems too. One problem is the human up there is a de-skilled human, because he doesn't do it anymore, as we just had with the grinding. He doesn't even know how. We have the problem with the pilots. You know, pilots now are, the planes are landing automatically. So the pilots lose the skill to land the plane manually. That's why they go into the simulator, and they have heavy simulator training not to lose that skills. But in all other my projects, I mean, expect the pilots and maybe the air traffic controllers, everybody else has no simulator. So they just lose the skills and don't have it anymore. And the other thing is the situation awareness. I mean, how does he know that he has to jump in? I always, when I'm reading a bit about the cars we are expecting now, who are driving fully automatically, I think that's really dangerous. I mean, as long as they can, then that's fine. But even if it is very seldom, when the human inside should intervene to prevent an accident, then this must happen very quick. And I cannot imagine anyhow that humans sit there for hours and being highly attentive and not doing anything. They start talking, looking around, playing with the children. They will not have the situation awareness to protect the situation. One more thing in this domain is that what we also see is that the technology starts controlling human behavior in terms of telling the human what to do and how to do it, which, let me be a little bit cynical, the engineers find a good thing, because then the human do what they want them to do. But what we see here too is a problem that the people not only lose the know-how, because the know-how is in the machine, but it is communicated to them, but they especially lose the knowing why. They learn from the machine what to do and how to do it, but they don't know anymore why they do it. And we have seen accidents where people did do the things right, but it was not the right thing, and they didn't understand. So they don't know anymore why they do the things. They just follow recipes. And, and that means that they cannot judge whether they're on the right way or on the bad way. The technology also gives information very often to the humans. For example, airplanes are highly automated nowadays, and there is a lot of information from the system in the cockpit coming to the pilots. So we asked pilots at Zurich Airport, 223 pilots we were asking, and these are all commercial pilots flying all the machines we are traveling with, and not the private pilots, but pilots in different airlines, Western airlines, flying Airbuses and Boeing airplanes. So we asked them, did you experience wrong sensor reading during your flight? 27% say, never, I experienced that. Did you experience a wrong activation of a warning system during your flight? It's 19% that said that never happened. And that's the worst, I think. Did you experience unexplainable events coming out of the automation to you? And it's only a third of the pilots that say that didn't happen to me. And when we're talking to the engineers, I mean, sometimes the pilots are right, sometimes they are wrong, they just don't understand. But psychologically, it doesn't make a difference. For them, it's just unexplainable. And that has an impact on trust in automation. And there we see that different kind of trust in automation that comes out of such experiences, and that triggers also different kind of mistakes. For example, the commission error means a wrong information coming from the system is considered right. And it's very difficult if you don't know knowing why anymore to judge whether the information is right or wrong. And even if it happens only seldom. Or the omission error is there is a miss in action, so the human is not doing something because the system doesn't give him an information. And that's also a problem. But on the other side, we also have distrust in automation. The perceived happens probably even more often, that the human perceives the system unreliable and doesn't trust it anymore. And that means the human does not follow even the right information. And also we have this information that the human considers disturbing. It's called nuisance information. Nuisance information is an information that actually is right, but it's of it's not of interest for you at the moment. And for example, when I work with my computer and I want to delete a file, then there comes an alert, and the alert asks me, do you really want to delete that file? And the first time I read it, I say, yes, yes. And then next time comes in, yes, yes, yes. And I start not reading the alerts anymore. I just click them away. And the 50th alert might be a totally different alert that wants to alert me for something different, and I don't read it, and I click it away. And we will find the same things also in cockpits, highly automated planes. Now let me go on a higher level, the level of not human machine, but social system technological network interaction. We were investigating, as I was also presenting this morning in a session, a planning process, planning and scheduling of order throughput through organizations. This is a rather schematic scheme. The idea is that we have a production company and the orders are running through the production units. And it can be dozens or hundreds, and then they can be in different companies if it is not one company, but if it is a supply network. And, and somehow this is controlled. And when we want to understand how it is controlled, we go into the company and want to find out how do they really control it. Not how it is written in the management handbooks or in the process description, but how they really do it in everyday life. And there we see, for example, that of course there is a computerized network that interconnects people. And the network itself has some intelligence in it that also produces plans. But there is also and I'd like to emphasize very much on that, there is also a social network where people are talking to each other. And in that social network, we have formal structure, like formal meetings where they coordinate, but we also have informal structures because just they know each other. We found situations, for example, in one company, Swiss SME, where somebody, like it is shown here, is in the communication network. He does not have access to the computers, but he is very central in the communication of that unit. And often these are people who do not have a formal task in planning and scheduling, but for example, and that really happened in one SME, it's just the worker in the interimistic stock, because they are producing, then it goes to the stock, and then the next is producing. And the guy at the stock, he sees his shelves and realizes, there is something wrong. Normally we have parts there, today not. And he starts asking, why is there no part? And they found out problems like that are never in the IT. And also we see, for example, people who just know direct passes. He is not talking to anybody. There is no blue line to any of his colleagues, but he is overpassing that hierarchy directly up here because the two of them know each other for 20 years, and before he was up here, he was down there, and they were working good together, so that's how they know each other. And that's a good thing, not to be misunderstood. This interaction of that red and that blue network actually controls the order flow. And what we see here sometimes is that there is a new release or the introduction of a new business software, taking the old red out, putting a new red in, and the performance decreases, although you have better computers and better systems. And our hypothesis would be it decreases because the new red doesn't fit anymore to the old blue, and the system together does not perform jointly anymore. So that are my examples. Now I would like to switch to the positive contribution humans have to system performance and what we learn for the design principles, always from a psychological point of view, of course. And I don't assume that this is the only important point of view, it's just my point of view. And we have to work together interdisciplinary in order to design these systems. I'm just a little bit summing up what I was presenting in the examples I was showing. So on the individual level, we have skills, knowledge, expertise, knowing why. We have situation awareness. We have motivations, commitment to motivation or commitment to what they do. We have many more human positive contributions that we would like to see when the system is performing. And on the organizational level or on the level of designing processes and communication and distributed decision-making processes in the company, we would like to have an organization that can cope with variances, disturbances, that is resilient against disturbances on a local level, so that if I have a problem here, it does not promote to somebody else who will suffer from the problem but cannot do anything against the cause of the problem. And we will have an organization that tunes all the different action of the people and that combines knowledge of the different people so that it is not only a sum of the knowledge, but so that the combination of the knowledge creates more than the two people not cooperating could create. So that's what we're asking for on the two levels, and also here we could have many things more. My point is, for example, the skills that it's not just coming from magic. So we have to design the systems in a way that the skills and the tacit knowledge and the experience we want the humans to have so that they really can develop them. So we need a task design, so we are very much focusing on the human task. And is the human task designed in a way that, for example, the skills or the experience can be developed when performing that task? And if the machine is always running automatically and I'm always out of the machine and I'm not involved, then I cannot develop that experience. If the machine or me as a company do not need that experience, then that's fine. But if I want or if I need the experience, then I have to make sure in the task design that people can develop that experience. Same about motivation. I mean, motivation very often is attributed to the person as if the personality would be motivated or not. And partly, of course, that's true. But motivation is always an interaction between person and context. And what we design is not the person. It's very difficult to change people. So what we design is their context. And when we design boring tasks, we must not wonder when the people are not motivated, because you cannot be motivated for a boring task. So we need to design a task that motivates people. And I now give you example for task design on different levels, on the level of the individual task, on the level of human-machine interaction, or the function allocation, and on the task design of tasks for organizational units. And I have just some spots, just to give you the idea how we approach it. I start with the individual task. So, for example, the aim is to have a motivated workforce. And we know from psychology, and you see it's not new, we know from psychology for quite a while that there is some precondition to have intrinsic motivation. And intrinsic motivation defined as the human is interested, is committed, is engaged, cares for what he does. Because that's the precondition that he really can bring his positive contribution. Now, in order to have intrinsic motivation, we need, according to that model, we need some psychic states, they say. So the people must psychologically be in a certain state, and if it is not given, I am just not motivated. And the state is, I must perceive meaningfulness in what I do. I must perceive responsibility in what I do, and I must experience or get information about the result of what I do. And very important is the perception. So if I have his responsibility, that's written in the job description, that's not enough. Whether or not I perceive responsibility or not, it's something totally different. Now, talking about task design, we have some developed, or they have developed criteria for how we should design the task in order that these psychic states can emerge. And I just go into some of the criteria. Completeness of tasks means I must have both. The task must be complete in terms to have a closed loop between doing and thinking. I do what I do and I think about what I do. That must be closed, because when I take it apart, like we have in Taylorism, or if I do the thinking to the white collar and the doing to the blue collar starts not knowing anymore why he is doing what he is doing, and he loses meaningfulness. So in order to have perceived meaningfulness, we need, for example, completeness in task design. And now that means we have to design the organizations and also the technology the human works with in a way that human does not lose completeness of what he is doing. Just making a disclaimer, all that I say is only important if I really consider the human important resource in my production. If I don't consider the human, if I don't want motivation, then it's no problem if I don't do that. But then maybe I have other problems, and especially, let's say, our economy in Switzerland, whatever can be fully automated away from the human is 10 minutes? 5 minutes. Everything that we can do design that can be fully automated, that goes away to China or to India or wherever. We cannot keep it in Switzerland. So what we need, what we keep in Switzerland is the brain work actually, and so we need to design the system accordingly. Okay, when coming for a human-machine functional location, we developed our self-models. We want human control over automated systems. Again, we have preconditions. Humans are in control over automated systems only if they understand what is going on, if they predict what can happen in the future, and if they can influence the course of happening. So when I drive my car, I must understand not the engine. For that, I have the mechanic. I must understand the driving process. I must have an understanding of speed and time it takes to brake, and how I do my turning and what my controls are for. And I will have to predict in car driving maybe some seconds, in other tasks some days or weeks before, and what can happen, and I must influence. So we must design the machines in a way, for example, that the human has process transparency, we call it. And process transparency means he understands what is going on. And this cannot be fully shifted to training. Right? You cannot fully automate a task and explain in the classroom to human how it works. They must be involved in what they do. Huh? That's very important. Okay, and coming to the last topic, so how do we design tasks of organizational units? Also there we have criteria. For example, I took now the aim of resilience, because it's the topic we are discussing very much at the moment. Resilience is defined as the intrinsic ability of a system to adjust its functioning prior, during, following changes and disturbances, so that it can sustain required operations under expected and unexpected conditions. And that means nothing else but the system must be able to adjust to dynamics, and not only to those dynamics we are prepared for, we must also be prepared to be unprepared, to be able to react in situations where maybe the accident escalates, and therefore we are relying on the human competencies and the way we organize them. And one aim is to have local control of variances and disturbances. And again, we have design criteria for the task now, not for individuals, but for teams or for organizational units, so that they are independent of each other, that they have opportunities to internally regulate variances and disturbances and so on. So that's what we are aiming at. Let me just, with my last slide, sum up. When talking about socio-technical systems, what we are looking for is to a joint optimization of the social system and the technical system. And what is very important from a psychological perspective is that the rules, so to speak, of the social system totally different from the technical system. And when we optimize the technical system only, even if it is from an engineering point of view, the best possible technical system, if it doesn't fit to the social system, then the overall performance will not be good. So we must fit them together, and our approach to fit them together is designing the task that comes out of, for example, of technical design for human as individuals or for humans as collective in a way that is psychologically meaningful and creates the preconditions we need that the human can contribute to system performance. That's all the references. Many thanks for your attention.